Hello everyone. Today I'm going to present you chapter 13 of chemistry and which is about state of matter. This chapter has four subtopics. The first one is the nature of gases, and the second one is the nature of liquids, and the third one is the nature of solids, and the last and the fourth section is change of states. So in the fourth section of this chapter, what we're going to see is the nature of gases. When we look at this chapter and to understand clearly about the nature of gases, there are some key questions that we need to answer, and I'll read these key questions and before I go into the detail of this section. So the first key question is, what are the three assumptions of the kinetic theory as it applies to gases is question number one. And the second question is, how does kinetic theory explains gas pressure? And the third question is, what is the relationship between temperature and the temperature in Kelvin and the average kinetic energy of particles? These are the three questions that we need to answer when we go through this section. So to go through this section, a few things that I would like to say is, so far from what we know or what we learned in classes, we know what gases are, we know what solids are, and we know also what liquids are. And there is a similarity between them, and there is also a difference between each of these states of matter. So the first thing that you all have to remember is, when we talk about gases, one of the things that we already familiar with is our weather. The weather we live in, or the condition of atmosphere around us, since it is determined by the gases in our atmosphere, so the behavior of these gases, of course, will be affected or changes by the temperature of the surrounding and the pressure of the surrounding. So the atmosphere is a gas, and the factor that determines the behavior of these gases are mainly temperature and pressure. So once you know that gases flow from the area of high pressure to the area of low pressure, which tells you that uh, the difference of pressures in different area affects how things behave or how gases behave. And the next thing that we need to know is the kinetic theory and a model for gases. What model do we use for to describe gases, and how do we mention gases is the thing that we carefully have to remember, and need to have some model to understand what the gases are, which means a physical representation. What do we use to physically represent gases is a question. So but before we go into that, there are three questions that I raised at the beginning. And the first question is, what are the three assumptions of the kinetic theory as it applies to gases is what we have to look at. But before we go into that, when we talk about kinetic theory, what does kinetic mean? Kinetic means it means a motion in short, which refers to the word motion. So when we talk about the kinetic energy of substances, we are talking about the energy of substances due to this motion or because of it is a motion. According to the kinetic theory, all matter consists of tiny particles that are in a constant motion, which we call them atoms. Everything is made of atoms. These atoms are always in a constant motion, whether it is a solid substance, okay, whether it is a box or different shape of bags, which is hexagonal bags, or maybe a liquid water. Each of these substances or the air that we breathe, all of them, they are composed of a tiny particles called atoms, and each of these atoms are always in a motion. So the particles in gases, as you know from what we discussed so far, gases could be an atom, it could be a molecule. Example, the atomic gases are uh, helium, neon, argon, krypton, xenon, and radon, which are group 8 elements of the periodic table, they are all atoms and they are all gases. But other ones, which we consider gases as a molecule, are hydrogen, H2, nitrogen, N2, fluorine, F2, chlorine, Cl2, carbon dioxide, carbon monoxide, sulfur dioxide, nitrogen monoxide, and so on. We can list thousands of molecules that are still gases. So when we apply the kinetic theory of gases, or the kinetic theory directly to gases, there are very important assumptions that this theory tells us. And the first assumption is the particles in gases are considered to be small. It is small. I'm showing you a particle, a kind of something spherical, but this is not small, just to show you that it is hard sphere, something that is hard sphere and small, that has insignificant volume. So what does each of these points mean? The gas particles are very, very small in size. The model is hard sphere. So if you have to draw or come up with the model of a gas, you have to come up with something that is spherical in shape and hard, and that has insignificant volume. What do you mean when we say insignificant volume? Remember what we discussed about 1 mole of a gas contains 6.02 times 10 to the power of 23 molecules, which is exactly equal to 22.4 liters if that condition is at STP. So when we say 6.02 times 10 to the power of 23 molecules occupying 22.4 liter, but if you take 22.4 liter divided by the number of particles in 1 mole, which is divided by Avogadro's number, it gives you a very, very insignificant volume. That is why we say a gas has insignificant volume. Its volume is, you can ignore it. It is negligible. Within a gas, the particles are relatively far apart. So if you consider this as 2 particles of gases, these 2 particles are far away from one another, and the distance between 2 particles is 10 times larger than the size of the particle. The distance is 10 times, which means each gas particles are 10 times smaller than the the distance between the 2 particles, the 2 particles. And the other concept that you need to again understand, and that this key point is, between the 2 gas particles, there is empty space. There is empty space. So that is why gases are compressible. So if you apply pressure on it, you can compress it. You can reduce the volume occupied or the space occupied by gases. And the other point is, there is no attractive or repulsive forces exist between gas particles. The 2 gas particles, they don't attract and they don't repel each other, according to the kinetic theory of gases. And the second point, or the second assumption of the kinetic theory, is the motions of particles in a gas are rapid, constant, and random. What does it mean? The gas particles move at a rapid speed, at a high speed, at room temperature. The gas molecule, let's say if you take nitrogen, has an average of 343 meters per second. The same thing for oxygen molecules. But the heavier the gas, the slower it is, because the mass of substance, of course, affects their masses to have a certain or always a constant average kinetic energy. But other than that, every gases are rapid. They have high speed and their speed is constant, and they move also in a random direction, which means they don't travel in a straight line always. What happens is, when the 2 particles travel in air, let's say each of them moving at the speed of 343 meters per second, and then when this one travel this way and this one go this way, at one point they collide. After collision, they each change their direction. This might move in this direction, and the other one might move in totally different direction. So, but before collisions, let's say if this molecule is moving this way, this one is moving this way, until they collide, both of them, they travel in a straight line, but after collision, they change their direction. So every single time when they collide with the neighboring molecule or with the wall of the container, they change their direction. That is why we call the direction in which the gas particles move is random. And because of this random motion, and because there is no force of attraction between the gas particles, gases fill the containers regardless of the shape and the volume of the container. Let's say if I have one, let's say small amount of gas in this small container, and if I transfer the gas in here into this one, which is much more larger container, or into this one, which is really much more even bigger, or anything larger, it will fill. So what does it mean? Gases do not have fixed volume. So an uncontained gas can spread out in space without limit. So if you look at this picture now, what you see is the molecules are traveling at rapid speed and rapid speed or at high speed, and you see that they are colliding. Some of them, they are colliding right there. It shows you a collision right there. There is a collision between particles, and then after collision they move in a different direction. So initially anything that is moving this way, probably after collision it will move in any direction that is unpredictable. So the rapid and constant motion of particles in a gas causes them to collide with one another and with the wall of their container. They don't just collide with one another. There is a chance or high chance for them to collide with the container of their wall too. The particles travel in a straight line, passes until they collide with another particle. So this particle travel this way until it collides with this one, and then it can travel that way until it collides with another particle. The particles change direction only when they rebound from collisions. Other than that, they travel in a straight line. As you see, the second diagram shows you there are straight lines, but after collision, they change their direction. All collisions between particles in a gas are perfectly elastic. When two objects collide, there are two types of collisions in general. Sometimes objects collide and then they move apart after collision. Sometimes objects collide, they stick together after collision. Just based on that, you can say that if two objects collide and then after collision they move apart, you can simply easily understand this. You can say, oh, that is a type of elastic collision. But if the two objects stick together after collision, and if they stick together and they move together, you can consider them easily as inelastic collision. So there are also, we can also consider as elastic collision as a perfectly elastic collision, of which the gaseous molecules show. So the collision between gaseous particles or gases are perfectly elastic, which means during an elastic collision, kinetic energy is transferred without loss from one particle to another particle. Let's say if particle A is moving from left to right, when these particles move from left to right, the other one is moving in different direction, the two particles might be of the same size or of different size. It could be nitrogen colliding with oxygen, or oxygen colliding with oxygen, or nitrogen colliding with nitrogen. We know that based on the type of the molecule, their size is not the same. So what happens is when one molecule of air collides with with another molecule of air, the energy will be transferred between them from one substance to another substance without any loss in the form of heat or in the form of sound, which that is what elastic collision means, which means the total kinetic energy remains constant, which is also can be stated as energy is conserved during elastic collision. So an elastic collision is the one in which the kinetic energy is transferred from one particle to another particle with no overall loss of energy or kinetic energy. Kinetic energy cannot be lost during this time, during elastic collisions or during the collision between gas particles. And the next thing that we need to understand, or we need to know, is the gas pressure. To understand about gases, we need to understand how the pressure of gases behave. One thing that we need to know is what is pressure. Pressure will be calculated by pressure equals to force over area. When you deal with the pressure, we calculate pressure by dividing the force over area, and therefore the unit of pressure is the unit of force over the unit of area, which is Newton divided by meter squared. The ratio of Newton to meter squared is called Pascal. So Pascal is SI unit of pressure, and sometimes it is measured by kilopascal. Kilo is a prefix, which means 1 kilopascal. 1 kilopascal is 1000 Pascal. So the question that you have to answer under this subtopic of gas pressure is, how does kinetic theory explains gas pressure? Gas pressure is a pressure that results from the force exerted by gases or a gas per a unit surface area of an object, which is force over area. So moving bodies exert a force when they collide with another body. So gas pressure is the result of billions of rapidly moving particles in a gas simultaneously colliding with an object. So if we have a gaseous molecules in this container, the gas molecules that are in the container, they usually collide with the container or with this bottle, and so that it will exert a pressure on it. So the pressure inside this container will be calculated by the force that the gaseous molecules exerts on it and divided by the surface area. That is what is known as pressure. If no particles are present, let's say if we vacuum this container, or if there is no gaseous particle that is in this container cannot have this shape, because there is no, even when there is no gas molecules or any air in it, this will collapse because there is no pressure that keeps this container to be to stay as this beautiful shape. So what happens is, if you remove all the gases, an empty space with no particles, no pressure, is called vacuum. Air exerts pressure on the earth because the gravity holds the particles in air within the Earth's atmosphere. You know, the gravity of the Earth doesn't hold just liquids and solids to the Earth, but it also holds our atmosphere to the Earth, so that the atmosphere will not evaporate. The collisions of atoms and the molecules in air with objects results with atmospheric pressure. So the atmospheric pressure, which we usually call it 1 atm or 760 millimeter of mercury or 101.3 kilopascal, is the result of the collision between the gaseous molecules or the gaseous atoms with the Earth or with objects on the Earth. So atmospheric pressure decreases as you climb. Now some of the things that you see is, when you climb from low altitude to high altitude, what you can see is the pressure decreases. That is why when you climb a mountain, you have to breathe deeply. That deep breath is because of low density of air at higher altitudes. So as you climb to a higher altitude, or maybe to the top of the mountain, the density of air decreases, which means the chance of collision between the air molecules and the airs or with the objects around also decreases. That decreases atmospheric pressure. A device that we use to measure atmospheric pressure is known as barometer. So as you see on this picture, this barometer is the first barometer that is made of mercury, and the mercury is the bowl is filled with the liquid mercury, and a tube that is vacuumed was inserted upside down. It's vacuumed means there is no gas particles in it, means there is no pressure in the tube initially. When you insert that tube upside down, because of the pressure, you see the red arrows are the pressure from the atmosphere. The atmospheric pressure push down this liquid mercury. It exerts pressure on the mercury. Since there is no pressure inside the tube, now the liquid will be pushed up through the column of the tube in the column, and that will rise to a certain extent, and finally it stops. So if you do this experiment at sea level, the mercury will be supported to about 760 millimeter, so in the column of mercury. But if you do the same experiments at the second picture on the top of the Mount Everest, which is about 9,000 meters above sea level, as you see, look at the size of the arrows. Those arrows are smaller than the arrows on the sea level. That means there is what? Less atmospheric pressure, and this atmospheric pressure can support only mercury for about 253 millimeter of mercury, which is almost what? It's much more less than half of the pressure at sea level. The issue or the difference between the two places is the density of air. Lower air density at higher altitude, and so that the pressure at higher altitude is lower than the sea level. So the other thing that we need, or you guys need to answer, is about weather forecasters. How can we meteorologists forecast the weather condition of a certain region, which means usually how do they know that the storm is coming, or how do you know what is going to happen is based on the pressure of the surrounding. So remember that wind always blows from the area of high pressure to the area of low pressure, and that tells you, based on the pressure of the surrounding and the temperature, that helps meteorologists to predict the weather conditions of the area where you live or any area in the world. So one thing that you all have to know is when the storm approaches, the column of the mercury of the previous slide, it goes down, indicating that the pressure or the atmospheric pressure decrease. So the other thing is, I talked earlier about how we can measure the pressure, and we say that the SI unit of pressure is called Pascal. Pascal is a ratio of Newton to a meter squared. Normal atmospheric pressure, at sea level is about 100,000 Pascal, which is 100 kilopascal. If you take the last three zeros, and those last three zeros will be turned into kilo, so kilo means 1,000. And there are also other units that we can use to measure pressure. These are very common units, which is a millimeter of mercury, which can be written as mmHg. Hg is the symbol for mercury in a periodic table. And the other unit is atmospheres, which is ATM in short. One standard atmosphere, or 1 ATM, is a pressure required to support 760 millimeter of mercury in a mercury barometer at 25 degrees Celsius. When the temperature of the surrounding at sea level is 25 degrees Celsius, if you measure the pressure, the atmospheric pressure will support the mercury for about 760 millimeters. So 1 ATM means 760 millimeters of mercury, which is also equals to 101.3 kilopascal. One thing that you all have to be careful is when we say one standard atmosphere, we are not saying this is exactly the same as STP, which we call it standard temperature and pressure. We remember, during standard temperature and pressure, let's say, for example, at STP, we say that the volume of 1 mole of any gas is 22.4 liters. That is when the temperature is 0 and the pressure is 1 or 1.3 kilopascal, or 1 atmosphere, or 760 millimeter. But in the case of a standard atmosphere or ATM, when we say 1 ATM supports 760 millimeter of mercury, it is not at 0 degrees Celsius, it is at 25 degrees Celsius. Keep that in your mind. Now, once we know that we have different types of units of pressure, we have to have the ability to convert one unit of pressure to another unit. For example, convert 450 kilopascal 2 atmosphere and millimeter of mercury. So what we need to do is in this in the case of word problem that has some numerical issues or numeric problems, remember to follow the 3 steps: analyzing the problem, and once you analyze the problem means identifying what is known and what is unknown. As you see, we know that the pressure is 450 kilopascal, and we also know that 1 atmosphere is 101.3 kilopascal, which is also equals to 760 millimeter of mercury. But we ask her to convert 450 kilopascal to atm and millimeter of mercury. So when you do this one, that means you are analyzing your problem. And then the next thing is you need to figure out what conversion factor can we use. So from the relationship between atm and kilopascal and atm and millimeter, or kilopascal and millimeter, you can write the conversion factor that you need, which is the ratio of 2 equivalent units. As you see, to convert kPa to atm, we have 1 atm over 101.3 kilopascal as a conversion factor. But to convert kilopascal to millimeter of mercury, we use 760 millimeter of mercury per 101.3 kilopascal. By using either this or the inverse of this, we will convert a given 450 kilopascal to a prescribed unit. So, and you take 450 kilopascal multiplied by the conversion factor. Kilopascal cancels kilopascal, and then the remaining unit will be atm. And therefore, if you multiply 450 times 1 over this number, it will give you 4.4 kilopascal. Remember, this number has 2 significant figures, and the final answer must have 2 significant figures. On the same time, again, when you go to part B, 450 kilopascal, kilopascal has to be at the bottom in a conversion factor, and then the new unit, which is millimeter of mercury, has to be on the top. Then kilopascal cancels kilopascal. 450 times 760 divided by 101.3 will give you 3400 millimeter of mercury. You can write this by scientific notation as 3.4 times 10 to the power of 3 millimeter of mercury. So then you can evaluate your work. Does this answer make sense? Because the first conversion factor is much less than 1. And the second is much greater than 1. If you look at those conversion factors, it makes sense that the value expressed in atmosphere and the millimeter of mercury respectively is smaller and larger than the values expressed in kilopascal. So your work is right. That is how you evaluate your work. So the other thing that you all need to again answer is the checkpoints. Let's check you if you understand what we did so far. So one of the questions by which you can check yourself is, what is the pressure in millimeter of mercury inside a vacuum? So I'll give you 1 minute, 1 second. I'm sorry, 1 second. So within 1 second, you have your answer. Okay, write down your answer on a paper. So did you say 0 millimeter of mercury, or 0 atm, or 0 pascal? If you say all those, you are right. And before you go to the next concept, and you can pause this video at this point, and you can go to page 422 of chapter 13. There are practice problems at the bottom of the page, problem 1 and problem 2. Practice those questions and see if you can convert those units of pressure. And then saying that, once you did those 2 examples, you have to go to the next page on your textbook page 423. You can read it, but let's go through it. The next slide will give you information about the kinetic energy and the temperature. What is the relationship between temperature and Kelvin and the average kinetic energy of particles? This is the same question that I raised at the beginning of this section. So now we'll go through it and make sure that at the end of few slides, you have to answer this question. As a substance is heated, its particles absorb energy, and some of which, of course, are stored within the particles. So some of the energy when you hit something, some of it will be stored, some of it will increase its speed of motion. So this stored portion of energy is called potential energy, and this potential energy does not raise the temperature of the substance. So the remaining absorbed energy does speed up the particles, and therefore it increases the kinetic energy. This increase in the kinetic energy results in an increase in temperature. When the kinetic energy of something increases, it is temperature also increases. Remember, when you go to the gym, when you run around, gradually as your body moves, as you try to run faster or more time, your body temperature increases. And the same thing with particles. So that is one thing that you guys have to connect. The average kinetic energy. So what is average kinetic energy? Let's say if you take a water. This is a water molecule in a beaker. So in this beaker, there is a large amount of water molecules in it, but it's about 500, it's close to 400 ml. Yeah, it's about 450 ml. This is about 450 ml, but it's a huge number of molecules in it. We know that 1 mole of any molecule is 6.02 times 10 to the power of 23 molecules. Now the question is, what is average kinetic energy? The average kinetic energy is the energy. Now let's say if you consider each of these water molecules and you calculate the energy of each of them, and then you finally add them together divided by the number of particles, that gives you the average kinetic energy. So the particles in any collection of atoms or molecules in a given temperature have a wide range of kinetic energies, which means in this water, not every molecule of water has the same kinetic energy. Some of them, they have high kinetic energy. Some of them, they have low kinetic energy, but the majority of them, they have somewhere in between the highest and the lowest, which is a kind of average kinetic energy. So what you guys have to remember is there are, let's think about again the molecules on the surface again. The molecules of the surface of this water are the one that can evaporate, which means they have high kinetic energy, but the others remains in the form of liquid. That means they have low kinetic energy. But the majority of them, they have energies somewhere in the middle of this range. We use average kinetic energy when discussing the kinetic energy of a collection of particles in a substance. At any given temperature, for example, at room temperature, the particles of all substances, regardless of the physical state, whether it is solid, liquid, or gas, have the same average kinetic energy. So the average kinetic energy of the particles in here is the same. The average kinetic energy of the particles of gases in this bowl is the same. The average kinetic energy of the particles of this is steel, all the particles in steel, they have the same kinetic energy. So, and again, I have a cork right here, which is a solid substance, so it has particles in it. So the average kinetic energy of the particles in a cork are also the same. But not every particles in it have the same kinetic energy. The average, we are talking about the average kinetic energy. So if you look on the next slide, it shows you the distribution of the kinetic energy of water molecules at two different temperatures. So there is a green one and the purple one. The green one shows the distribution of molecular kinetic energy at low temperature or in cold water, and the purple one is showing you the distribution of the molecules of water at high temperature. So a green, as you see, if you look at the majority of the molecules on the hot one, they have higher kinetic energy. If you look at the purple one, you see most of them, they have very high kinetic energy, but still very few of them, they have still very high. But if you come to the green one, very few of them, they have low kinetic energy, somewhere around here. Some of them around here have high kinetic energy, but the majority of them are still in somewhere lower kinetic energy. So compared to if you compare the two curves with the cold water, And with the hot water molecules have higher average kinetic energy than the cold water. The average kinetic energy of particles in a substance is directly related to the substance's temperature, which means the temperature of substance and their kinetic energy is both of them are directly related, which means if one increases, the other one increases. So an increase in the average kinetic energy of particles causes the temperature of substances to rise. The decrease in the average kinetic energy of molecules decreases the temperature of the molecules. As a substance cools down, let's say, for example, what happens is the particles tend to move slowly and their average kinetic energy decreases. When you heat a substance, the particles start to move faster and then their average kinetic energy increases. So the absolute zero, I hope you guys know what 0 Kelvin means, which is equals to negative 273.15 degrees Celsius. It is the temperature at which the motion of the particles theoretically stops or ceases. So if we can drop the temperature of any molecule, gas, liquids, or solid to absolute zero, what happens is their temperature drops, means the particles stops. At that point, these particles, the particles of which their temperature is at absolute zero, they cannot give out any kinetic energy. So, and again, from our previous discussions of units of temperature, we said that, if you guys remember, the minimum temperature that we can reach on absolute scale is 0. But the degree Celsius can be negative and degree Fahrenheit can be negative too. But there is no negative temperature on absolute scale or Kelvin scale. So absolute zero have never been produced in the lab, by the way. And what scientists did is they approached to 0.1 nano Kelvin, which is 1 times 10 to the power of negative 10 Kelvin, but they never got to 0. So that means no scientist reached to absolute temperature so far. That tells you that there is a lowest limit of temperature, even though there is no higher limit on temperature. The coldest temperature recorded outside the laboratory are from space. Astronomers used a radio telescope to measure the temperature of boomerang a nebula, and they measured that it is up to 1 K. The temperature at that point is 1 Kelvin. It is the coldest known region in space. The Kelvin temperature of a substance is directly proportional to the average kinetic energy of particles of substances. Remember, we are not saying degree Celsius or degree Fahrenheit or any other unit of temperature. What we are saying is the average kinetic energy of particles is directly proportional to the energy of the average kinetic energy is directly proportional to the Kelvin temperature, which is not other units. Be careful about it. So let's check what we discussed so far. What is the results of increasing the temperature of a gas sample? A decrease in average kinetic energy. B, no effect on the sample. C, an increase in average kinetic energy of a sample. D, particles slow down. What happens? Think about it. Did you get your answer? Let's see what the answer is. Increasing the temperature of a gas increases the average kinetic energy of the sample. So it has effect on it. We said that the temperature in Kelvin scale is directly proportional to the average, which means if one increases, the other one increases. If one decreases, the other one decreases. Any question? All right. So these are the areas where you have to critically think and do these practice problems. Answer the following questions or solve the following questions. If you need to answer them. If you need to solve them. So read each of these questions and try to answer them. And once you answer them, and you will go to your mastering, your Schoology. In Schoology, you have assignments, which is 13.1. You do the questions from that once you master this, but do not go to those questions until you master these questions. Or if you have any question, and please send me email. I'm always open. I will respond to your questions as fast as possible. Thanks so much. Have a good day.